Word embeddings are how computers pretend they understand English, by turning every word into an impressive-looking list of numbers and calling that meaning. These numbers then hang out together in a vast digital space, quietly judging how similar they are to each other. Cat and dog are best friends, while quantum sits alone in a corner, wondering why nobody gets it. You might think turning words into numbers is easy. Let's just give every one of our 50,000 words a number. Cat is 9, dog is 72, and quantum is 30,452, obviously. The problem is, these numbers mean absolutely nothing. Sure, each word has its own shiny number, but they don't say anything about the word itself. It's like assigning every person on Earth a random phone number and pretending you've captured their personality. A sequence like 4, 52, 175, 30, 452, and 1875 tells you nothing, except maybe that whoever invented it should not be left alone with a spreadsheet. Basically, we need to encode more than just a word's name. We need to encode its meaning. So instead of giving each word one sad little number, what if we gave it a whole set of them, each capturing a tiny piece of its meaning? Maybe one number for sweetness, another for roundness, another for probably edible, and maybe one for how likely it is to explode if you microwave it. If we had enough of these properties, we could find apple just by describing it. Sweet, round, edible, solid, and deeply disappointing if you thought it was chocolate. And that's the clever trick behind word embeddings. We represent every word as a vector, which is just a fancy way of saying a list of numbers that make you sound smart at dinner parties. Each number or dimension captures one of those hidden properties. The beauty of this approach is that words which mean similar things end up sharing similar properties. In other words, their coordinates in this weird numerical universe are practically neighbors, possibly borrowing sugar from each other. Even small changes to these properties can shift a word's meaning. That's the magic of embeddings. They turn math into meaning, or, depending on your perspective, meaning into math, which somehow sounds both profound and depressing. For example, USA and America should be close together across every dimension. If they're not, your model's probably having an identity crisis. The same goes for film and movie. Film says I'm cinema, and movie says pass the popcorn, and the embedding says you two are literally identical. So now we've got this brilliant idea. Words as vectors with thousands of numbers each. Fantastic. Except how exactly do we get those numbers? Well, it's a lot easier said than done. Let's pretend we'll sit down and define every property needed to describe every word. You'd need a complete grasp of language, a catalog of all worldly properties, and a neat partitioning scheme so they don't overlap. And that's before the hard part, teaching a computer to rate every word on every property, which is like asking a blender to write poetry. Take roundness. Sphere gets a perfect score. Basketball, also very round. Football, hairy territory. In the US, it's a stretched potato with self-esteem issues. Everywhere else, it's a soccer ball, gloriously round, but also a sport where roundness matters far less. So which number does football get? Good luck with that. Doing this for every word isn't just daunting, it's unscientific, and most likely gloriously wrong. We need a different approach. The best way to actually build these vectors is to learn them from the absurd amount of text humanity has already produced. Books, articles, the entire internet, and yes, even the comment sections. Buried in all that chaos are the properties we want. We just have to dig them out. One particularly clever idea, called word2vec, is both brilliant and almost suspiciously simple. The trick is to build a small neural network whose only job is to learn what words tend to appear near each other, and from that, somehow, mathematical representation of meaning starts to emerge. Here's what the network does. It takes a few words as input, let's say 5, and tries to guess the middle one from the 4 words surrounding it. So your input words are these 4 outer words. The output is the middle word. Between the input and the output is one hidden layer, the mysterious region where all the math, confusion, and magic quietly unfold. Think of the word-to-vec model as a kind of translator. It learns how to translate words into meaning and back again, using only one simple goal. Given a few words, guess which word fits best in the middle. Here's how it actually works. We take all the text we can possibly get our hands on, books, websites, articles, everything, and break it into windows of 5 words at a time. We hide the one in the middle and feed the others into the network as input. In the middle of the network, we put a layer of neurons, one for every embedding dimension we want to learn. If we plan to represent each word with 15 numbers, that means there are 15 neurons in this hidden layer. Now, the input layer has 1 neuron for every word in the vocabulary, about 50,000 in English. Each of those neurons connects to all 15 neurons in the hidden layer through a unique set of weights. The word the, for example, connects to the 15 neurons through its own 15 weights, WV1 through WV15. The word cat has its own set, and so does every other word. Spoiler, those weights are exactly what become the word embeddings. So here's what happens. Take the phrase, "the cat sat on mat." We treat sat as the target word, the one we're trying to predict, and the other 4, the, cat, on, and mat, as context. We start by setting every input to 0, except for the words we're considering. For those 4, we set their inputs to 1/4, so together they average to 1. The network takes that input, computes the activations in the 15 hidden neurons, and then produces an output, one value for each of the 50,000 possible words. We then adjust the network using backpropagation, telling it that sat should be 1 and every other word should be 0. Then we repeat, over and over for billions of word combinations. At first, the network just produces nonsense, but as training continues, the weights start to organize themselves in a meaningful way. And here's the beautiful part. Those very weights, the connections between words and the hidden neurons, are the embeddings. They're what make the network capable of choosing the right middle word. To make this intuition crystal clear, let's walk through a concrete example. Let's say you feed the network the phrase, "the movie looked amazing." When we run the network, we set every input word to 0 except the ones actually in the window. Any word whose input is 0 contributes nothing to the hidden layer. Its weights have no effect. In our example, 3 of the 4 context words stay the same, the, looked, and amazing. Their contributions to the hidden layer are fixed. The only thing that changes is swapping movie with film. Now, if the network is still going to predict trailer as the missing word, the total signal going into the hidden layer must stay almost identical, because that total signal is what determines the model's output. Since 3 of the 4 contributing words are unchanged, the only way for the hidden layer to receive the same overall signal is for movie and film to send nearly the same signal themselves. And the only way that can happen is if their weights, the connections from the movie neuron and the film neuron into the hidden layer, are extremely close to each other. That's why it becomes clear that these learned weights, the W's, really capture the meaning of words. They encode how words behave in context. They encode meaning.